So this won't take long at all, unless you really want it to. The addition today is so there's a couple more pushes that we have to make with absolute values. The easier push is today. This is simple. There's no way this doesn't go well. I should not say that. I should knock on wood when I say it. The harder push is when we start throwing variables onto the other side. That gets a little bit more complex. But today we're just introducing two new special cases to this. So I've been avoiding them to this point. But one of them is something like this. Let's say we had 5 times the absolute value of x minus 2 plus 6 is greater than negative 4. So it just looks like a regular old problem, and we know what to do first, which of course is to subtract 6. So if we subtracted 6, because we want to get the absolute value by itself, we would be left with 5 times the absolute value of x minus 2 is greater than negative 10, right? And then what's the final step? Divide by 5. And this takes us back now to the topic of what do we do when there's a negative? And again, I've been avoiding those, and Delta Math didn't have any of them for you on. I don't know how many of you are done with that assignment, but you should not have seen any weird ones at all. So that's why I made you a paper worksheet today, because I wanted to have control and force it to give you some of these that we're going to learn about. If we divide by 5, we get the absolute value by itself. And we have the absolute value of x minus 2 is greater than negative 2. So if any part of the lesson doesn't go well, it'll be this part where you cannot get through this if you're not thinking. Like some math, you can just watch and transcribe and memorize the process. This one, you have to think. And it's not complex, nasty, hard. It's just you have to think with me. What is always true about absolute value? Like, say again. Right. So like if I sat here for an hour and I took this thing in the yellow circle and I just kept plugging numbers in place of x, like 50, negative 16, 0, negative 42, anything you want. And then when I'm done and I go whatever number I put in and I subtract 2, and then here's the kicker, I take the absolute value of whatever that is. Like Kaysen said, it will never produce a negative. Do we agree? And I mean never. Absolute value does not ever produce negative outcomes. Having said that, what can we say about the absolute value being greater than negative 2? And that's the word I'm looking for. Always. You got that quick. It will always be greater than negative 2, won't it? And what we're used to, I think where the difficulty comes up is we got used to with equations when it's an equals negative 2 or negative something, we just instinctively jump in and write, well, no solution. But in this case, it's actually the dead opposite of that. Not only is that not correct, it's the dead opposite of correct. What we want to say here is that I could not make this not work. I could ask a fourth grader to say, okay, pick a number and try to solve this. And kid goes, I don't know, 4. And the kid puts in a 4. And guess what? The absolute value of 4 minus 2 is, come hell or high water, going to be greater than negative 2, is it not? So we don't look at a problem like this as one that we have to split and find boundaries. We look at it very logically and say, this always works. For that reason, the solution is all real numbers. We cannot say that we have any place on the number line where we draw a boundary and say, well, everything to this side works or everything between here and here works. Literally every number on the number line from negative infinity to positive infinity would solve this problem. So this is what your solution actually looks like, all real numbers. And the way we graph an all real numbers situation is it's a little bit silly, but you have a number line. And rather than doing what we're used to, which is making boundaries and drawing circles and stuff like that, you actually just take a bare naked number line like this and you just code it completely with shading. So we take a number line, no need to put any numbers on it, and we just show the world that, look, I am shading the entire number line from left to right. And again, that is because I could not ever in a million years find a number that does not make this come out true. Does that make any sense? Good. Now, on the other side of the coin, there's problems like this. And the reason I put 13x plus 521.8 is because, as you'll see, that really serves no purpose in the outcome that we're going to talk about here. So what's inside the absolute value? Like in that last problem, we never even had to discuss the x minus 2 because it's a non-issue. It just doesn't matter. We have no control over the situation. How do we get the absolute value by itself here? Right. And if we divide by -4, we of course have to remember to flip that Pac-Man around, right? So a greater than, what looked like it was going to be a greater than problem is actually a less than problem. And we're left with the absolute value of I don't really care is less than -3. And you don't have to write IDRC in your notes. Like you can actually put 13x plus 521.8. But my point is this. Again, we could sit around here for an hour. Not that we would, that would be nuts, but we could sit here for an hour and keep putting numbers in place of X. And how often would the answer to that absolute value come out to being something that's less than -3? Never. And you hit the two words I was looking for today right away. Always on the last one and never. And never is a very powerful word. We're not saying it's probably not going to happen. We're saying it cannot happen. Absolute value as a function, as a machine, is not capable of producing negative numbers. So the question is, how could I ever make it come out to be something less than -3 if I can't even make it be negative at all? And again, the answer is I can't. Therefore, the answer to this problem is that there is no solution. And you can spell out no solution if you like writing words, or you can use the symbol in mathematics that represents having no solution, which is a circle with a slash through it like this, which is often why I tell kids not to cross zeros. I know some people, when they write zeros, they slash them. Very infrequently do people do that. But this is why we don't want you doing that, because then the zeros with the slashes start looking like empty sets. That's what we call that. It's the empty set. It means if I listed the set of numbers that solve this problem, there is nothing in the set, hence that symbol. So that's what we use for no solution. And the graph, does that make sense? So those are your two new special cases for the days for today. And I did sprinkle them. I kind of distributed them throughout today's assignment. You'll see a couple of each, I believe. I think a couple of each. So the graph of this is, it's honestly kind of like the last one, pretty silly. This one's actually even sillier than the last one. How do you think I make a number line and then graph no solution? You don't do anything to it, right? You just literally leave the number line just sitting there. And that's how we show the world that, hey, I present to you my graph of the solutions for this problem. And it's just nothing. There's nothing on the number line. So if you leave a number line untouched, it's no solution. And if you cover the whole number line with arrows on both sides, it's all real numbers. That makes sense? Nice short, sweet lesson there. So the rest of the time, 34 minutes, I think you have to work on the one I'm going to hand out. Um, or to work on the one or both, work on the one from yesterday. Got it? You'll pass it out for me? Thank you. Appreciate it. I'm going to let you guys settle this. You guys